Welcome to AP Chemistry at Hananiga High School. Today we'll be starting Chapter 4 and we'll be looking at the first two sections, Sections 4.1 and 4.2. And Chapter 4 deals with aqueous reactions and solution stoichiometry, solution chemistry. So we're going to apply the idea we talked about last chapter with stoichiometry to solution situations. Now, Chapter 4 along with Chapter 13, because they're related ideas. When you take a look at those two chapters combined, because those are the two solution chapters, about 9 questions out of the 75 in the multiple choice section on the AP test come from these ideas. And on the FRQ section, there's a question almost every single year. So this is an area of chemistry that's heavily represented on the AP test. So between these two chapters, there's a lot of information that you need to be familiar with. Now, section 4.1 deals with general properties of aqueous solutions. And remember, as you're watching the movies, it's the first time you've really been doing this along with the notes. Remember, as you're watching the movie, you need to be filling the notes out. Those will be collected tomorrow and points will be awarded for it. So don't forget to take your notes using the note sheets that I gave you. If you need to, pause the movie and go back and rewind and re-listen to a section again, but I think it'll be a fairly easy set of notes to do here today. Now, solutions are defined as homogeneous mixtures of two or more pure substances. The solvent is present in the greatest abundance, and all other substances would be solute. Now, if you go back to what you were probably told in middle and elementary school, the solvent does the dissolving, the solute gets dissolved. That's an oversimplistic view. Um, it would be true that when you have a smaller quantity and it's going into a larger quantity, it's going to disperse more. So that simplistic viewpoint does sort of work, but the easier way to look at it is solvent is there in greatest abundance and all others would be considered solute. Now, dissociation is a term that is related to this. When an ionic substance dissolves in water, the solvent pulls the individual ions from the crystal and solvates them. They used to be associated, and now those ions are dissociated and go off into solution. So this process is what's known as dissociation. Now, solutions in which water is the solvent are called aqueous solutions. And most of the time, the solutions we're looking at are going to be water solutions. So most of the time, we're looking at dissociations of solutes into water as a solvent. Now, one thing that can change when you're dissolving substances in water is the conductivity of the water. All aqueous solutions can be classified in terms of whether or not they conduct electricity. Water itself, pure water H2O, does not conduct electricity to any great degree. But with the dissolving of certain types of solute in the water to make an aqueous solution, they will conduct. Other solutes don't cause the water solution to conduct. An electrolyte is a substance that dissociates in ions when it dissolves in water. So an electrolyte is basically a substance that dissociates in ions. So we're talking about ionic compounds when they dissolve in water. They form ions in solution, so they would be classified as an electrolyte. And if we're going to look at the conductivity situation, we'll often look at what's happening from an electrolyte point of view. These solutions conduct electricity when it's an ionic compound that's dissolved in water because now they can carry electrons. And you end up with a transfer of electrons, um, and we call that conductivity. So if you end up with a movement of charge, and once you have charged particles in the water, you can have a movement of charge, you end up conducting electricity. A non-electrolyte may dissolve in water, but it doesn't dissociate into ions, and therefore it can't carry charge. So therefore, it doesn't cause the solution to conduct electricity. So since they don't conduct electricity, they are known as non-electrolytes. So non-electrolytes, when they dissolve, don't cause the water solution to conduct electricity. So when ionic compounds dissociate, the solid no longer exists as a well-ordered group, and they're surrounded by molecules in the process known as solvation. So when we're looking at an ionic compound dissolving, or even a molecular compound dissolving, as the compound dissolves in water, it becomes surrounded by water molecules and pulled off into solution. That process is known as solvation. The water molecules surrounding the ions stabilize them and prevent the anions and cations from recombining. And that's a really important concept for you to understand. Because remember, opposites attract. So when we have cations and anions, so here we've got in solution a cation and an anion. If I go back to the picture we were just looking at here, here we do have in solution cations and anions. Those things, when they come close together, you would think they would reassociate and recrystallize. But the water that surrounds it helps prevent that from happening. So water plays a very important role. Besides the fact that it is dissolving the particles surrounding and pulling off a solution, it impedes the reassociation of those particles and stabilizes solution. Now, most molecular compounds don't form ions and won't allow electrical current to flow, and therefore they would be non-electrolytes. So molecular bases and acids are going to be electrolytes. So when you have substances that are acids and bases dissolving in water, because they are forming ions in the water solution, they will be electrolytes. So NH3 ionizes in water to form NH4 and OH minus. This is something you looked at last year in the last chapter of pre-AP chemistry. You looked at how acids and bases associate with water in acid-base reactions to affect the pH. Well, they also, as they dissolve in water, cause the water to conduct electricity. A strong electrolyte dissociates or ionizes completely. So an electrolyte is a substance when you put it in water, it causes the solution to conduct electricity. Well, you can create great conduction or minimal conduction. So some or a lot. Well, a strong electrolyte is something that dissociates or ionizes 100%. So you end up creating a great number of ions. So you do a better job at carrying charge. So a strong electrolyte is a substance that dissociates completely. So they conduct electricity very well. On the far right here, you have a situation where there's many ions in solution, so it does a much better job at conducting. So that would be what a strong electrolyte looks like. Now, when you have a substance that's a strong electrolyte, it's dissociating 100%. So really the solid NaCl doesn't exist anymore. It's becoming 100% ion, Na plus and Cl minus. So when you're looking at a strong electrolyte reaction, a key that it's a strong electrolyte reaction is the fact that you have a single arrow shown. So this is really a better representation of what you really have when you have an aqueous strong electrolyte. You don't have NaCl solid and H2O. What you really have is sodium ions floating around in water and chloride ions floating in water. And this is really how it would be written in an ionic equation, because that's what you're doing in an ionic equation, is showing a representation of how these species really exist. So what you've got here on the right here is really a better representation than saying NaCl aqueous. NaCl aqueous implies the Na and the Cl are still stuck together. Now, strong electrolytes can, one, be strong acids. And remember, you need to memorize these. We already had a test over this. So one of the reasons you've got to know this is for this chapter. When you have one of these acids in water, you know it's going to be a strong electrolyte. Strong bases are also strong electrolytes. Once again, you had to memorize the strong bases. It's the group 1 and the heavy group 2 hydroxides. Remember the CBS? So all those strong acids and strong bases make strong electrolytes. And soluble ionic salts. If you have an ionic compound that's water soluble, it's going to break apart 100% of the ions, and you're going to be a strong conductor of electricity. And what this really is looking at is what we were talking about with our solubility rules. So soluble ionic salts are strong electrolytes. So strong electrolytes are basically strong acids and bases and your soluble ionic substances. So what you're looking at here are the different things that will form strong electrolytes whenever they are with other cations. So these are things you must know, and that's why you got to memorize your solubility rules. So one of the reasons for the AP chemistry you have to memorize solubility rules is for chapter 4. It's going to come up again in 3 or 4 other chapters in AP chemistry alone, let alone the AP chemistry test. Now, those are strong electrolytes. Weak electrolytes are substances that dissociate or ionize only partially when dissolved in water. And these would be things then that make water conduct electricity poorly, which is what you see in the middle picture here, because you have fewer ions in solution. Now, reactions of these types of substances are typically shown with a double arrow, because not only do you make the products and you get these ions, but those recombine and go back to make your reactants. So you're not ionizing 100%, you're only partially becoming ions, and that's because it's a reproducible or reversible reaction. So weak electrolyte uh, reactions are written with a single arrow when you're looking at the dissolving process and what's happening. And that's because really, if it only dissociates 10%, 90% of what you have is in your molecular form over here, which in this case is the weak acid, acetic acid. So in this particular case, as a weak electrolyte, the molecular form of the substance, it together as a group, is really a better representation of what you've got. So that's why when you do net ionic equations, you don't dissociate your weak acids because most of it is going to be still associated. So you have a lot more HC2H3O2 in that container than you have H plus and the acetate ion. Now, weak electrolytes are going to be your weak acids and bases. And that's why you got to know your strong acids and bases, because if they're not a strong acid or base, then they are a weak electrolyte. Ionic substances, if they're water soluble, then they dissolve in water and they're going to break apart 100%. They're going to be your strong electrolytes. Molecular things can be your strong acids, are molecular substances, but yet they disassociate 100%, so they become strong electrolytes. But your weak electrolytes, ionic stuff, that's never going to form a weak. Um, but your weak acids and bases would fall in that category. Now, your non-electrolyte category is really just going to be molecular substances that aren't strong acids or bases or weak acids or bases. All other molecular compounds are going to be in the non-electrolyte category. And it's another reason why it's so important you know your strong and weak acids and be able to identify something as an acid or a base or a molecular substance. So how come strong bases aren't on the list? Well, because technically strong bases would really be over there in our ionic category, and that's where we would place them. So we're still looking at ionic substances, ionic compounds. So that's why you only see the strong acids in the strong electrolyte, because technically the strong bases are incorporated with ionics. Acids are molecular that we're looking at, and strong acids would dissociate 100%, which makes them strong. Now, next section gets into precipitation reactions. You should remember these from pre-AP as your double replacement reactions. So that's really what we're going to be looking at here as a way to think about that. We're going to look at it from more points of view than you did last year, but in the end, double replacement stuff last year, that's going to fit in what we call precipitation reactions here. When one mixes ions that form compounds that are insoluble, as you'd predict by the solubility rule. So if you look at the two compounds that would form in a double replacement reaction, if one of them is insoluble, then a precipitate is going to form. And what you're seeing here is a precipitate of the bright yellow solid lead iodide. Now, the solubility of substance is the amount of substance that can be dissolved in a given quantity of solvent. A substance with a solubility of less than 0.01 is considered insoluble. So when we say something is insoluble, most people think, oh, that means it doesn't dissolve at all. No, it means it dissolves to lower than a 0.01 mole per liter amount. And most everything has some solubility. It's just in many cases it's incredibly, 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 incredibly low. But technically anything that's under 0.01 molar would be considered insoluble. Because remember, moles per liter is big M, molar. For precipitation reactions, you have to know your solubility rules. You have to identify if something on the product side is going to be insoluble or not. So you have to know your solubility rules for this. Now, the scientific name for what we're looking at here with exchange reactions is called metathesis. So what we called double replacement last year is really an example of what's known as a metathesis. Metathesis comes from the Greek word meaning to transpose. So last year, for those of you coming from honors chemistry, this should look familiar. You have two aqueous substances coming together in a double replacement reaction. You end up with an exchange of ions. The Ag used to be with the NO3, and now it's going to be with the Cl, and the K used to be with the Cl, and now it's going to be with the NO3. We have a double replacement occurring. So Ag gets together with AgCl plus 1 minus 1 makes 1-to-1 AgCl. K gets together with NO3 plus 1 minus 1. The formula then becomes KNO3. But based on your solubility rules, KNO3 is aqueous. It still stays dissolved. But AgCl, that's an insoluble substance by our solubility rules, so that's going to end up being a solid. So you need to know how to do the transpose or double replacement that you did last year, and you also need to be able to identify what ends up forming the solid. Now, the general form of this type of reaction can be written this way, and this should look familiar from last year. So this is typically what a metathesis reaction would look like. Now, many precipitation acid-base reactions exhibit this pattern. So acid-base neutralization reactions, as well as our precipitation reactions will follow this pattern. Now, if you're going to be predicting metathesis reactions, you really need to follow these three steps. First, you're going to identify what are the ions. Then you're going to put the cation from one reactant with the anion from the other. Don't forget to use the ion charges to predict the subscripts of your new chemical formulas. Every time you make a new chemical formula, you have to derive the formula of that new ionic compound based upon the charge of the ions that are now together. And once you've done that and you have your valid chemical formulas on the product side, then you go through and you balance the equation. Now, when writing equations for aqueous reactions, it's often useful to express the reactions in several different ways. And this is something you should remember if you took honors chemistry. If you took regular chemistry before this, there's going to be some new information here. First of all, the easiest way to represent what's happening in a double replacement reaction is what's called the molecular equation. And that's basically what you get when you balance the double replacement reaction. It's technically what's called a molecular equation. You're showing everything as associated together in their molecular form, whether they really exist that way in solution or not. From there, you can split into the ionic equation, which really looks at exactly what you've got before and after. And then finally, you would cancel to get the net ionic equation. And that's a process in honors chemistry you went through. Now, the molecular equation is really, it lists the reactants and products in their molecular form. Regardless of whether KNO3 really exists as K is stuck to NO3s in aqueous solution, you're showing the association that is KNO3 as that ionic compound. And you're doing the same thing for AgCl, but since it's a solid form here, it was a precipitate, it wasn't water soluble, those things are actually associated together. So that is an accurate representation of exactly how that thing would exist. Well, when you're doing this, you're doing your double replacement and you're balancing the equation, what you're actually writing is what's known as the molecular equation. It's the reactants and products in their molecular form. Doesn't mean AgNO3 and KNO3 are molecules. What I'm saying is molecular form, chunked as a unit. In the ionic equation, all strong electrolytes, which would be strong acids, strong bases, and your soluble ionic salts, are disassociated into their ions. And that's because that's how they really exist. They've disassociated 100% into their ions if they're a strong electrolyte. So AgNO3, well, that's a water-soluble substance, so it really doesn't exist as AgNO3 aqueous. It's Ag plus floating around and NO3 minus. KCl was aqueous, same thing. It's actually K plus and Cl minus floating around. And our product side, AgCl, well, that's an insoluble ionic substance. That's a non-electrolyte. It stays in its molecular form, AgCl. And KNO3 was aqueous. That's because it's water soluble, so that also dissociates in K plus and NO3 minus. Now remember, weak electrolytes and non-electrolytes are written in their molecular form. So insoluble ionic compounds as well as weak electrolytes and non-electrolytes are going to stay in their molecular form. So what's really happening here is a more accurate reflection of how the species exist both before and after mixing. Now the net ionic equation is a way to cut to the chase and simplify all the garbage and look at, okay, molecularly and on the particle level, what really happened chemically. So it's getting rid of all of the things that aren't really participating in the reaction and looking at exactly what is chemically reacting. So to form the net ionic equation, you cross out anything that does not change on the left side and right side. Those are called spectator ions. They observe the reaction happen or spectate. They're not a part of the chemical reaction. And the only things left in the equation would be those things that are actually changing or reacting during the course of the reaction. And what we're left with here is Ag plus and Cl minus are forming AgCl. From a chemical point of view, that's all that really happened. The potassiums and the nitrates that were there, they didn't do anything. So they weren't really a part of the chemical reaction. So when you're writing the net ionic equation, you're really getting to the heart of what really is the chemical reaction. The molecular equation that we wrote is really an oversimplification because not all the species are actually involved in a chemical reaction when we wrote that molecular equation at the beginning. So what you're really doing is in the ionic equation, you're writing everything as it really exists. And in the net ionic equation, you're canceling out all of the spectator ions, the things that really aren't participating in the reaction. And what you're left with then becomes your net ionic equation. So to sum up, when you're writing ionic equations, first write the balanced molecular equation. So do your double replacement, check your charges, predict your new compounds, and write them on the product side, and then balance. And then anything that's a strong electrolyte, you disassociate and break apart into its ions. And then at that point, you have the ionic equation, and then you cross out anything that remains unchanged, left side and right side, and you are left with the balanced net ionic equation. So what's left is your net ionic equation. So those are the steps you use in writing the net ionic equation. And that ends our first set of notes over chapter 4.